Something is moving through the darkness between stars. You can't see it with your naked eye, not yet, but right now, at this very moment, telescopes across the globe are locked onto a visitor that refuses to behave like anything we've ever tracked before. It's not following the rules. Comets tumble, they spin, they reflect light in chaotic, beautiful patterns as ice catches sunlight and gas streams behind them like cosmic hair. That's what they do. That's what they've always done. But this object, watch what happens when you plot its brightness over time. Watch how that tail moves. The patterns don't look random anymore. They look deliberate. There's a structure trailing behind it, stretching further than the distance between Earth and our moon. And it's not drifting. It's not flowing with the solar wind like it should. It's doing something that makes the equations uncomfortable. Something that makes scientists choose their words very carefully when they talk about it. December 19th, 2025. 48 hours from now. That's when it makes its closest approach to Earth. And before that moment arrives, you need to understand what we're really seeing, starting with something that should be impossible. Before we dive into the anti-tail, the structure that's rewriting the physics textbooks right now, make sure you're subscribed with notifications on. Over the next 48 hours, new data is coming in that changes the story with each passing moment. This isn't just another comet flyby. This is real-time science that's challenging everything we thought we knew about natural objects in space. You'll want to be here for every revelation, every piece of evidence that makes this visitor more mysterious. Because by December 19th, we might be looking at the universe very differently. Let's start with what you'd normally expect to see when a comet passes through our solar system. Picture a dirty snowball, chunks of ice mixed with rock and dust hurtling through space. As it gets closer to the sun, the ice begins to vaporize. The solar wind, that constant stream of charged particles flowing outward from our star, pushes this gas and dust away from the comet's head. It creates that beautiful tail we've all seen in photographs, always pointing away from the sun, always flowing backward along the comet's path like hair streaming behind a runner. It's one of the most reliable phenomena in astronomy, a law written by physics itself. 3I/Atlas should have followed that law. Every comet does. But when researchers first started analysing the detailed observations from observatories in Chile and Hawaii, something caught their attention. There was a tail. Yes, but there was also something else. A second structure. A faint feature extending in a direction it shouldn't. At first, they thought it was an optical illusion, something called an anti-tail. You see these occasionally when Earth passes through the plane of a comet's orbit. It's a trick of perspective. The dust scattered along the comet's path appears to point toward the sun instead of away from it. But it's not real. It's just how the angle plays with our eyes. They assumed that's what they were seeing. A curiosity, nothing more. Then they measured it. The structure wasn't an illusion at all. It was physical. It was massive. And it was behaving in ways that made absolutely no sense. A team of independent researchers, astronomers who'd been tracking 3I/Atlas since it was first detected crossing into our solar system, published their findings in a preprint paper that appeared on the ArXiv server just days ago. The title alone made people stop scrolling. The anti-tail of 3I/Atlas wobbled before perihelion. The measurements showed something extraordinary. This anti-tail structure extends for more than 400,000 kilometers. To put that in perspective, the Moon orbits Earth at an average distance of 384,400 kilometers. This tail is longer than that gap. Imagine a bridge of material stretching from where you're sitting right now all the way to the lunar surface and beyond. That's the scale we're talking about? But size alone wasn't what made scientists reach for their phones at 2 a.m. to call colleagues. It was the movement. Comet tails are passive structures. They're made of gas molecules and microscopic dust grains being pushed by radiation pressure and the solar wind. They drift, they flow, they respond to the environment around them like smoke from a candle flame, chaotic, turbulent, constantly shifting. They certainly don't move with precision. They don't maintain structural integrity across hundreds of thousands of kilometers. And they absolutely do not wobble. 3I/Atlas wobbled. The paper documented a series of oscillations detected in the antitail structure during the days before the object reached perihelion, its closest point to the Sun. These weren't random fluctuations that you'd expect from outgassing or rotation. The wobble was rhythmic, regular. The frequency was consistent down to measurements that made the data analysts check their instruments 3 times to make sure there wasn't a calibration error. Think about what that means physically. When you see a ship moving through water, its wake trails behind. If the ship turns, the wake curves with it. If the ship makes small course corrections adjusting left, then right, then left again, the wake wobbles. It records the motion of the vessel creating it. That wobble is a signature of deliberate movement. The antitail of 3I/Atlas was showing exactly that kind of signature. Dr. Avi Loeb, the Harvard astrophysicist who's become known for asking uncomfortable questions about objects that don't behave as expected, released a commentary that sent ripples through the astronomy community. He pointed out something crucial: a wobble of this magnitude, involving this much mass, requires a transfer of momentum. In simpler terms, something has to push back. If you're trying to stabilize an object or adjust its trajectory against the intense gravitational pull of the Sun, you make corrections, you apply force, you create exactly this kind of pattern in your wake. But here's where it gets even stranger. The wobble wasn't synced with the object's rotation. Most comets tumble as they move through space. They spin on multiple axes, irregular and unpredictable because they're not perfect spheres, they're lumpy, asymmetric chunks of ice and rock. If the antitail was simply responding to the rotation of 3I/Atlas, you'd see the wobble follow that tumbling pattern, but the frequency analysis showed something different. The oscillation was independent. It had its own rhythm, separate from how the main body was spinning. That should be impossible for a passive structure made of gas and dust. There's another problem. When you try to calculate the forces needed to make a cloud of gas and dust particles spread across a distance greater than the Earth-Moon gap move in synchronized oscillation, the numbers don't work. A structure like that should tear itself apart. The particles at the far end would be so loosely connected to the source that they'd simply drift away. There's not enough cohesion in dust and gas to maintain structural integrity at that scale while executing precise movements. Unless the structure isn't made of dust and gas. Unless it's something else entirely. Spectroscopic analysis, the technique where astronomers split light into its component wavelengths to identify what materials are present, started returning results that didn't match the expected profile of a comet tail. Yes, there were the signatures you'd anticipate: water ice, carbon dioxide, simple organic compounds. But there were other absorption lines in the spectrum, elements that are heavier, more complex, signatures that several researchers, speaking carefully and off the record, said looked less like a natural tail and more like what you might see in an exhaust plume. The kind of exhaust that might come from something using magnetic fields to channel plasma. You can see why people started choosing their words carefully, why press releases from major observatories began emphasizing the fascinating scientific opportunity that 3I/Atlas represents while avoiding certain questions entirely. Because if this tail isn't a tail, if it's a controlled structure showing signs of active stabilization and course correction, then we're not looking at a comet anymore. We're looking at something that was built, and it's been operational for at least the entire time it's been visible in our solar system, which raises a question that nobody wants to ask out loud, but everyone is thinking if it's under control. What is it doing right now? Because whatever it is, the wobble suggests it's not finished yet. If you've ever seen a photograph of a comet Hale-Bopp stretching across the night sky in 1997, or Neowise during that brief summer window in 2020, you've seen the tail pointing away from the sun. It's such a consistent feature that it's one of the first things you learn about comets. The solar wind pushes outward, the tail follows, it's automatic, predictable, written into the fabric of how our solar system works. So when astronomers from observatories in Australia and South Africa began comparing their astrometric data, the precise measurements of where 3 Ice/Atlas appeared in the sky at different times, they expected the anti-tail structure to align with the solar wind vector. That's the direction the charged particles from the sun are flowing. Everything gets pushed along that path. There's no exception to this rule in nature. The numbers came back wrong. The anti-tail was off by 12 degrees. 12 degrees away from where the solar wind should have pushed it. Now, if you're not used to thinking in astronomical terms, 12 degrees might not sound like much. It's less than the width of your fist held at arm's length against the sky. But in celestial mechanics, where we're tracking objects moving at tens of kilometers per second across distances measured in millions of kilometers, a 12-degree deviation is enormous. It's the difference between a river following its natural course and a river that suddenly decides to flow uphill. You can't have a passive structure, gas and dust, being blown by the solar wind, maintain a 12-degree offset from the direction of that wind. The physics doesn't allow it. It would be like holding a flag out in a strong breeze and having it point sideways instead of streaming backward. The flag doesn't have that choice. Neither should a comet tail. But 3 Ice/Atlas does. When the research teams plotted the vector of that massive 400,000 kilometer structure, when they extended the line to see where it was pointing, they found something that made the data sessions go very quiet. The anti-tail wasn't aligned with the solar wind, it was aligned with something else entirely. It points directly at the galactic center, Sagittarius A star. The supermassive black hole at the heart of the Milky Way, sitting roughly 26,000 light-years away from us. The same direction 3 Ice/Atlas came from when it entered our solar system. Think about that geometry for a moment. An object enters from the direction of the galactic core. It performs what looks like a textbook gravity assist around our sun, using the sun's gravitational pull to alter its trajectory. The same technique we use to slingshot our spacecraft to the outer planets. It stabilizes itself. It deploys this massive structure. And then that structure locks onto the object's point of origin, maintaining that alignment despite the solar wind trying to push it in a completely different direction. What does that sound like to you? It sounds like an antenna. A directional transmitter. A high-gain array designed to send information across vast distances with maximum efficiency. Dr. Loeb, in his follow-up analysis published just 48 hours ago, made a comparison that's hard to ignore. When we send spacecraft to the outer solar system Voyager, New Horizons, the missions that venture into the deep cold beyond Neptune, we equip them with directional antennas. These aren't broadcasting signals in all directions like a radio tower. They're focused. They point back at Earth with precision because when you're trying to send data across billions of kilometers, every degree of accuracy matters. You don't waste power scattering your signal into empty space. 3 Ice/Atlas is doing exactly what we would do. It's pointing home. But there's another layer to this that makes the alignment even more significant. The wobble we discussed, that rhythmic oscillation in the anti-tail structure, isn't random movement. When you analyze the frequency and amplitude of those oscillations, when you look at how the structure moves back and forth across that 12-degree offset from the solar wind, a pattern emerges. It looks like modulation. The technical term is frequency modulation, the same principle used in FM radio. You take a carrier wave, a steady signal, and you encode information into it by varying its frequency. The wobble in 3I/Atlas's anti-tail is varying at a rate that matches no known natural process. Not the rotation period of the object, not any harmonic of its outgassing cycles, not anything that would emerge from a tumbling chunk of ice and rock responding to solar heating. The frequency is independent, deliberate, and it's being encoded into the largest structure we've ever seen attached to an interstellar visitor. Several researchers, speaking privately because these observations haven't been peer-reviewed yet, have described what they're seeing as a data dump. Imagine you're a probe that's been travelling through a foreign solar system for months. You've been gathering observations, recording spectra, mapping gravitational fields, measuring radiation environments. You've collected terabytes of information. And now you're approaching the optimal transmission window, the moment when your antenna is fully deployed, when you have maximum power available, when the geometry is perfect for line-of-sight communication back to whoever sent you. You wouldn't transmit continuously. That would drain your power reserves too quickly. You'd wait. You'd position yourself. And then you'd send everything at once in a compressed burst, modulated into the most efficient signal format you could manage, that 12-degree offset. That's not the tail fighting against the solar wind. That's the tail maintaining a precise bearing despite the solar wind, the same way a ship's captain holds a course despite crosswinds and currents. You don't let the environment push you off target. You compensate, you adjust. You maintain your heading because your destination matters more than the path of least resistance. And 3I/Atlas's destination, or at least the destination of its signal, is the galactic centre, the place it came from, the place where, if you were going to have a receiver station capable of picking up a transmission from 26,000 light-years away, you might position it near a supermassive black hole, not because the black hole itself would receive the signal, but because the gravitational lensing effect around something that massive could amplify and focus incoming transmissions in ways we're only beginning to understand with our own observations of distant quasars. The anti-tail isn't breaking the rules of physics, it's following different rules. Rules that apply when you're not a rock, but a machine. When you're not drifting, but navigating. When you're not just passing through, but reporting back. And if it's reporting back, there's something we need to understand about what it might be saying, because the data it's gathering isn't just about the sun or the outer planets. It's been making measurements in a very specific region of space, our region. When you want to know what something is made of, when you want to understand the chemical composition of an object millions of kilometers away, you use spectroscopy. It's one of the most powerful tools in astronomy. Light from the object passes through a prism or a diffraction grating, splitting into its component wavelengths. Different elements absorb light at specific wavelengths, creating dark lines in the spectrum like a barcode. Hydrogen produces one pattern, oxygen produces another. Water ice has its own distinctive signature. You match the pattern, and you know what you're looking at. It's reliable. It's been tested against thousands of comets, asteroids, and planetary atmospheres. The technique doesn't lie. So when the spectroscopic data from 3I/Atlas started coming in from the deep field observatories in Chile, facilities equipped with some of the most sensitive spectrographs in the southern hemisphere, astronomers expected to see the usual suspects. Water ice, definitely. Some carbon dioxide, frozen into the surface. Probably traces of methane, ammonia, simple organic compounds, the standard mix you'd find in any comet that formed in the outer reaches of a solar system and got ejected into interstellar space. The first analysis showed all of those things. Water ice confirmed, carbon dioxide present. The basic building blocks were there. But then the spectroscopists noticed something in the absorption lines that didn't fit the model. There were features in the spectrum that shouldn't exist in a comet tail. Heavy elements, not just traces significant concentrations, iron absorption lines, magnesium, nickel, elements that are far too heavy to be vaporized and carried away in a typical comet's gas tail. You'd need temperatures of several thousand degrees Celsius to turn iron into a vapor. The surface of a comet, even at perihelion when it's closest to the sun, doesn't get nearly hot enough for that. We're talking about maybe 200 degrees Celsius at most. Iron melts at 1,538 degrees. It vaporizes at 2,862 degrees. So where are these heavy elements coming from? One possibility, the conservative explanation that several research papers have cautiously suggested, is that we're seeing dust grains, tiny particles of metal embedded in the ice being illuminated by sunlight. The metal isn't vaporized, it's just reflecting light. That would explain the absorption lines without requiring exotic temperatures. But there's a problem with that explanation. The distribution is wrong. When you have dust grains in a comet tail, they spread out, they form a diffuse cloud. The spectral signatures should be weak, scattered, inconsistent from one observation to the next as the dust moves and disperses. What the Chilean observatories are seeing is the opposite. The heavy element signatures are strong. They're concentrated, and they're remarkably stable across multiple observation sessions spanning several days. That suggests something very different. Not dust grains scattering light, but actual vapor, ionized gas containing heavy elements that's being somehow contained and directed within the anti-tail structure. How do you contain a gas cloud across 400,000 kilometers? How do you keep it from dispersing into the vacuum of space? There's really only one way: magnetic fields. If you've ever seen a video of NASA's plasma propulsion experiments, the electric thrusters being developed for deep space missions, you've seen what contained plasma looks like. It glows. It's held in place by powerful magnetic fields that shape the ionized gas into specific geometries. The fields act like invisible walls, channeling the plasma, directing it, preventing it from spreading out. It's the same principle behind experimental fusion reactors, where you need to contain plasma at millions of degrees without it touching the reactor walls. Several physicists who've been quietly analyzing the 3I/Atalus data have started using a specific term in their private correspondence. They're calling it a magnetic exhaust plume. Not officially, not in any published paper yet, but the term keeps appearing in emails, in Slack channels, in video calls between research groups, because that's what the spectroscopic signature looks like. Not a passive tail of gas and dust being blown by the solar wind, but an active exhaust ionized material being expelled through a magnetic nozzle. The kind of signature you'd expect from an advanced propulsion system. Think about what that means from an engineering perspective. If you're building a spacecraft designed to travel between stars crossing light years of empty space over timescales that might span millennia, you need efficient propulsion. You can't carry enough chemical fuel. The mass ratio doesn't work. You need something that can generate thrust for extended periods using the resources available in space itself. Hydrogen, the most abundant element in the universe. Solar radiation, the magnetic fields of stars. A magnetic plasma drive would let you scoop up interstellar hydrogen, ionize it, and accelerate it using electromagnetic fields. The exhaust would contain exactly what we're seeing: ionized gas with heavy element contamination from the reactor components. And it would need to be magnetically contained, or it would simply disperse uselessly into space. The mass ratio is another clue. When you calculate the total mass of material in the anti-tail based on the spectroscopic measurements and the brightness of the structure, then compare it to the estimated mass of the 3I/Atlas object itself, somewhere between a few 100,000 and a few million tons, based on its brightness and trajectory, the numbers don't balance. The tail appears to contain far too much mass for the size of the object producing it. Unless the object isn't solid, unless it's mostly hollow, a shell, a framework, a structure designed to maximize interior volume while minimizing mass, which is exactly how you'd build a long-duration spacecraft. You don't send a solid hunk of metal and ice between stars. You send the minimum necessary structure wrapped around the engines, the power source. The payload. Every spacecraft we've ever built has been mostly empty space inside. Comparing the density estimates, and these are very rough, based on trajectory analysis and brightness measurements, 3I/Atlas appears to have an average density somewhere between 0.1 and 0.3 grams per cubic centimeter. For reference, water ice has a density of about 9 grams per cubic centimeter. Rock is roughly 2.5 to 3 grams per cubic centimeter. Typical comets fall somewhere in between, around 0.6 grams per cubic centimeter. 3I/Atlas is significantly less dense than it should be, less dense than ice, which means either it's made of some incredibly porous, fluffy material that we've never encountered before, or it's not solid, it's hollow. It has internal cavities, spaces where something else could be housed, power systems, navigation, whatever was meant to survive the journey between stars. But if the spectroscopy and the density both point in the same direction towards something manufactured rather than natural, there's another piece of evidence that might be even more striking. Because 3I/Atlas isn't just showing a strange composition, it's showing a strange behavior in how it interacts with light itself. There's a basic principle in astronomy that's so fundamental, so obvious, that it barely needs stating. When an object gets closer to you, it appears brighter. A car's headlights in the distance are faint pinpricks. As the car approaches, those lights grow steadily more intense. The same applies to everything in space. As a comet moves closer to Earth, more of the sunlight reflecting off its surface reaches our telescopes. The brightness increases. It's simple geometry, it's inevitable. 3I/Atlas is doing the opposite. Over the past 3 weeks, as the object has been closing the distance between itself and Earth, moving from roughly 300 million kilometers away to its current position at around 270 million kilometers, amateur astronomers and professional observatories alike have been tracking its brightness. They've been measuring what's called its apparent magnitude, the measure of how bright an object appears from Earth. Lower numbers mean brighter objects. The full moon has a magnitude of about -12.6. The faintest stars you can see with your naked eye on a dark night are around magnitude 6. Comets typically brighten as they approach, dropping in magnitude, becoming easier to see. 3I/Atlas started at around magnitude 10 when it was first detected months ago. By all calculations, based on its size estimates and its trajectory, it should be magnitude 7 or even 6 by now. Bright enough to spot with a decent pair of binoculars. Bright enough that astronomy clubs would be setting up telescopes in parks to show it to curious families. Instead, it's magnitude 11. It's gotten fainter. It's dimming as it approaches. That shouldn't be possible, not without some extreme circumstance. If the object suddenly stopped outgassing, if it became completely inactive and stopped producing its coma and tail, you might see a slight decrease in brightness. But 3I/Atlas is clearly active. We can see the tail. We can measure the spectroscopic signatures of gas being released. It's not dormant. So where is the light going? The answer lies in something called albedo, the measure of how much light an object reflects. Fresh snow has an albedo close to 0.9, meaning it reflects about 90% of the sunlight that hits it. That's why snow is so brilliantly white. Charcoal has an albedo around 0.04, reflecting only 4% of incoming light. Most comets have albedos between 0.03 and 0.06. They're dark objects to begin with, made mostly of carbon-rich material and rock with patches of ice mixed in. But when a comet becomes active when it approaches the sun and starts vaporizing ice, creating that bright coma of gas and dust around the nucleus, the albedo typically increases. You're seeing sunlight scatter off tiny ice crystals and dust particles suspended in the gas cloud. It's like how clouds appear brilliant white even though water vapor is invisible. The scattering effect makes the comet much more reflective than the dark nucleus alone. The latest albedo measurements for 3I/Atlas, calculated by comparing the amount of sunlight hitting the object to the amount of reflected light reaching our telescopes, are coming back with values around 0.02 to 0.03. Lower than expected for an active comet. The object is absorbing roughly 97% of the light that hits it. Think about what that means. If you took a fresh comet, one that's been in the deep freeze of interstellar space for potentially billions of years, its surface covered in pristine ice, and brought it close to the sun where that ice begins to sublime and expose fresh layers underneath, you'd expect it to get brighter, not darker. You'd expect more reflection, not less. Unless the object isn't designed to reflect light, unless it's designed to absorb it. There are really only two reasons you'd build something with such a low albedo. Something that drinks in sunlight rather than bouncing it back into space. The first reason is stealth. If you want to minimize your visibility, if you want to pass through a solar system without drawing attention, you make your outer surface as non-reflective as possible. We do this with stealth aircraft and stealth satellites. We coat them in materials that absorb radar waves and visible light. Materials with carefully engineered surface textures that trap incoming radiation rather than reflecting it back to the observer. The technology exists. We've created materials called carbon nanotube arrays, sometimes called vantablack, that absorb 99.96% of visible light. They're the darkest materials ever created. Darker than coal. Darker than anything found in nature. From a distance, an object coated in this material doesn't look like a shape. It looks like a hole in space, a void where light goes in and doesn't come out. But there's a second reason to build something with extreme light absorption, energy collection. If you're a spacecraft traveling between stars, you have a fundamental problem power. Chemical batteries won't last. Nuclear reactors decay over centuries and millennia. You need something that can provide power for the duration of an interstellar journey that might span tens of thousands of years. The most practical solution is to harvest energy directly from the stars you pass. Solar panels, in their most advanced form, are essentially light-absorbing surfaces. They're designed to capture photons and convert them into electrical current. The more efficiently they absorb light, the more power they generate. Our best solar cells currently achieve around 40% efficiency in laboratory conditions. But there's no fundamental physical limit that prevents higher efficiencies with advanced materials and designs we haven't discovered yet. If the anti-tail structure we've been discussing, that massive 400,000 kilometer-long extension, is actually a deployed solar collector, a magnetic sail designed to harvest both light and charged particles from the solar wind, then it would appear dark. It wouldn't be reflecting sunlight back at us. It would be absorbing it, converting it into useful energy for whatever systems the object is operating. And right now, 3I/Atlas is in the ideal position for maximum power collection. It's past perihelion, its closest approach to the sun, where the solar flux, the amount of sunlight per square meter, was at its highest. It's been bathed in intense radiation for weeks. If you were going to charge your batteries, if you were going to fill your energy reserves for whatever comes after the flyby, this is exactly when you do it. The timing is remarkable. The object is dimming, absorbing more light precisely during the phase of its trajectory when solar energy is most abundant. And it's doing this while maintaining that perfectly aimed anti-tail structure pointing back toward the galactic centre, while executing those precise wobbles that look nothing like natural outgassing. It's collecting power, it's maintaining its transmission antenna, and it's about to reach the point of closest approach to Earth, the moment when all of this preparation might finally reveal its purpose. But there's something else happening in the light itself, something that goes beyond simple absorption and reflection, something that looks less like astronomy and more like communication. Amateur astronomers have been some of the most important contributors to comet science over the decades. They're the ones with backyard telescopes, with CCD cameras attached to computerized mounts, who spend cold nights tracking objects across the sky. They submit their data to international databases, brightness measurements, position updates, images that help professional astronomers who can't monopolize telescope time at major observatories. It's a collaboration that's been running for generations. When 3i/Atlas first became visible to amateur equipment, dozens of observers started collecting light curve data. A light curve is exactly what it sounds like, a graph that plots an object's brightness over time. For most celestial objects, these curves tell stories. A rotating asteroid produces a repeating pattern of brightness variations as different faces, some shinier, some darker, turn toward Earth. An eclipsing binary star shows regular dips as one star passes in front of the other. Even variable stars, pulsating from internal dynamics, create recognizable rhythms in their light curves. Comets typically produce messy light curves. They tumble irregularly. They have jets of gas erupting from different points on their surface as ice vaporizes. The coma, that cloud of gas and dust surrounding the nucleus, shifts and changes. If you plot the brightness of a normal comet over hours or days, you get a jagged line, chaotic, full of noise, random fluctuations that don't repeat. That's natural behavior for a chunk of ice and rock that's been wandering through space for millions of years. The light curve data for 3i/Atlas started appearing in the amateur observation networks about 2 weeks ago. At first glance, it looked normal enough. Magnitude readings hovering around 10 to 11 with some variation. But then, one observer in New Mexico, an engineer who'd built his own photometry rig and had been tracking the object nightly, noticed something odd in his dataset. The line wasn't messy, it was too clean. When he posted his findings to the online forums where amateur astronomers share data, other observers checked their own measurements. The pattern was there in everyone's data. The brightness of 3i/Atlas would hold steady, perfectly flat for a period of time. Then it would drop by exactly 0.4 magnitudes, hold steady again, then return to baseline, drop, steady, return, drop, steady, return. The drops were happening every 144 minutes, like clockwork. For perspective, 144 minutes is 2.4 hours. That's a very specific interval. It's not tied to Earth's rotation. It's not connected to any obvious orbital resonance in our solar system. And most importantly, it doesn't match any natural rotation period that would make sense for an object of this size. If 3i/Atlas was simply spinning, and we were seeing brightness variations as different parts of its surface rotated into view, you'd expect irregularities. You'd expect the period to vary slightly as the object tumbles, as outgassing creates uneven forces. Natural rotation isn't this precise. But a timer is. What makes this even more striking is the magnitude of the drops themselves. A change of 0.4 magnitudes represents a decrease in brightness of about 32%, not 30%, not 35%, exactly 32%. Within the measurement error of the instruments, that's a precise fraction. If you were designing a signal, if you wanted to encode information into variations in brightness, you'd use exact ratios. You'd make the pattern unmistakable. distinguishable from a random noise. Nature doesn't work in exact fractions. Nature is messy, probabilistic, influenced by countless variables. When you see precision like this, you're looking at something that's been engineered. The forum discussions exploded. Amateur astronomers started comparing their data sets, time-stamping their observations down to the second. The pattern held across different observers, different equipment, different locations on Earth. This wasn't an instrumental artifact. This wasn't a mistake. The object was genuinely pulsing in brightness with mechanical regularity. One astronomer, a retired telecommunications engineer in Australia, made a comparison that sent the discussion in a new direction. He pointed out that the pattern looked like pulse position modulation, a technique used in radio communications to encode digital data. Instead of varying the amplitude or frequency of a signal, you vary the timing between pulses. The gaps between pulses carry the information. What if the steady periods between brightness drops weren't just empty space? What if the duration of each steady period was the message? If you measured the length of time between drops, you might find variations. Some intervals might be 144 minutes, others might be 143 or 145. Those tiny differences, measured precisely, could encode binary data. A shorter interval could represent a 0, a longer interval could represent a 1. When several observers started analysing the timing with this framework in mind, something emerged from the data. The intervals weren't perfectly uniform. There were variations, small but measurable. And when you converted those variations into binary, creating a string of ones and zeros based on whether each interval was shorter or longer than the average, you got sequences that showed non-random structure, not the repetitive patterns you'd expect from a rotating object with a few bright and dark patches, but complex variations that looked more like encoded information. Now, to be clear, this is where we enter territory that hasn't been formally peer-reviewed. These are amateur observations, preliminary analyses, patterns that might or might not survive rigorous statistical testing. But the fact that multiple independent observers are seeing the same thing, that the pattern is consistent across different instruments and locations, suggests there's something real here. What makes this particularly striking is how it connects to everything else we've been discussing. Remember the wobble in the anti-tail, that oscillation occurring with precise frequency. When you overlay the timing of that wobble, the rhythm of the anti-tail's back and forth motion, with the timing of these brightness drops, they synchronize. When the tail swings to one position, the object dims. When it swings back, the brightness returns to baseline. That's not coincidence. That's a physical mechanism. The tail structure, just as it oscillates, is periodically blocking light from the main body. Or perhaps it's reflecting light in a way that creates a strobe effect, directing light away from Earth at regular intervals. Either way, you have a massive structure larger than the Earth-Moon distance acting as a shutter or a mirror, creating a signal that can be detected from millions of kilometers away. If you wanted to send a message that could be picked up by anyone with a telescope, this is how you'd do it. You wouldn't need a radio transmitter. You wouldn't need to aim a laser. You just use the star behind you as a backlight and create patterns in that light by carefully controlling what blocks it and what doesn't. It's elegant, it's efficient, and it's happening right now. As 3I/Atlas continues its approach toward the point where everything, the geometry, the timing, the energy reserve seems designed to align. But this careful preparation, these precise patterns, they're building toward a specific moment, a moment that's been planned into the trajectory from the beginning. There's a reason why space agencies spend years calculating launch windows for missions to Mars, Jupiter, or the outer planets. Orbital mechanics is unforgiving. You can't just point a spacecraft in the right direction and fire the engines. You need the planets to be in the correct positions relative to each other. You need the geometry to work in your favour. Miss the window by a few days, and you might have to wait months or even years for the next opportunity. The mathematics behind these calculations is complex, but the principle is simple efficiency. You want to minimise fuel consumption. You want to maximise the scientific return. You want everything trajectory, timing, power availability, communication windows to align at the optimal moment. December 19th, 2025 is that moment for 3I/Atlas on this date, at approximately 1423 Universal Time. The object will reach its point of closest approach to Earth. The distance will be roughly 270 million kilometers, about 1.8 times the distance between Earth and the Sun. In cosmic terms, that's intimate. That's close enough for detailed spectroscopy, close enough to resolve fine structure and images if we had spacecraft in the right position, close enough that light travel time is only about 15 minutes, but the proximity alone doesn't explain why this date matters so much. What makes December 19th extraordinary is the geometry of the alignment. On this date, Earth will pass directly between 3I/Atlas and the Sun. For a brief window lasting approximately 4 hours, our planet will be positioned along the line connecting the object to our star. It's not a perfect eclipse. 3I/Atlas won't pass through Earth's shadow. The angles aren't quite right for that. But from the object's perspective, Earth will appear to transit across the Sun's disk, similar to how we see Venus or Mercury occasionally cross in front of the Sun from our viewpoint. Why does this matter? Think about radio communications. When NASA's Mars rovers need to send data back to Earth, they don't transmit constantly. They wait for optimal conditions. One of those conditions is minimizing solar interference. The Sun is an incredibly powerful radio source, flooding the inner solar system with electromagnetic noise across a wide range of frequencies. When a spacecraft is transmitting and Earth is on the opposite side of the Sun, or nearly so that solar noise drowns out the signal, it's like trying to have a conversation next to a jet engine. The solution is to wait until the geometry improves, until the Sun is not directly between the transmitter and receiver, until there's a clear line of sight without the star's interference disrupting the signal. December 19th provides exactly that geometry for 3I/Atlas. If the object is transmitting data back toward the galactic center, and everything we've discussed suggests it might be, then having Earth block the Sun during the transmission window would significantly reduce noise. Our planet, from the object's perspective, creates a brief shadow in the solar radio flux, a quiet zone. A moment of maximum signal clarity when data can be beamed through the solar system with minimal interference. But there's another factor that makes this date even more significant: gravitational lensing. Einstein's theory of general relativity tells us that massive objects bend space-time. When light passes near something very massive like a star or a planet, its path curves. This effect has been observed countless times. We see it when distant galaxies are magnified and distorted by massive galaxy clusters between them and Earth. We see it during solar eclipses when stars appear slightly out of position because their light is being bent by the Sun's gravity. The same principle applies to any form of electromagnetic radiation, including radio waves. If you position a transmitter, a planet, and a distant receiver in the right alignment, the planet's gravity can actually focus and amplify the signal. It acts like a lens. NASA has proposed using this effect for future deep space communications by positioning spacecraft on the far side of the Sun, using our star's immense gravity as a natural signal booster for transmissions to the outer solar system and beyond. On December 19th, for those 4 critical hours, 3I/Atlas will have the opportunity to use Earth's gravity in exactly this way. If it's transmitting toward the galactic center, towards Sagittarius A star, 26,000 light-years away, and it times the transmission to occur when Earth is directly in the path, our planet's mass could lens and amplify that signal. Not by a huge factor. Earth is tiny compared to the Sun, but every bit of gain matters when you're trying to send data across a quarter of the galaxy. The precision required for this is extraordinary. The object would need to know Earth's orbital position months in advance. It would need to adjust its own trajectory to ensure the alignment occurs at exactly the right moment. And it would need to time its transmission, that data dump we've been inferring from the anti-tail modulation, to coincide with the peak of the lensing effect. That level of planning doesn't happen by accident. When NASA sends spacecraft to the outer planets, mission designers spend years calculating every detail. The Voyager missions, launched in 1977, took advantage of a rare planetary alignment that occurs only once every 176 years. The trajectory was planned to use gravity assists from Jupiter, Saturn, Uranus, and Neptune in sequence, a cosmic billiard shot that required precise timing and positioning. If Voyager 2 had launched a few weeks earlier or later, it would have missed the alignment, and the grand tour of the outer solar system wouldn't have been possible. 3I/Atlas is executing a similar level of precision. It entered our solar system on a trajectory that brought it past the Sun at exactly the right angle and distance. It's been active deploying its anti-tail structure, modulating its signals at exactly the right times. And now it's approaching Earth during a window when the geometry provides maximum transmission efficiency. This isn't opportunistic. This is designed. And there's one more element to consider. The object isn't just passive during this alignment. The data we've been tracking, the wobble frequency, the brightness modulations, the spectroscopic signatures, they're not static. They're changing, accelerating. The pattern is building towards something. As December 19th approaches, as the geometry aligns and the power reserves fill from solar collection, the object is spinning up its systems. The heartbeat is getting faster. Whatever mechanism is creating these signals, whatever process is controlling the anti-tail's movements, it's intensifying, and that acceleration, that building energy, suggests something crucial. The object isn't finished with what it came here to do. The alignment on December 19th isn't an ending, it's a beginning. Or perhaps more accurately, it's a culmination. The moment when all the preparation, all the careful positioning and power collection finally serves its purpose. But purposes can take many forms. When engineers design spacecraft, they build in safeguards for the moments of highest stress. Launch, when the vehicle is fighting against Earth's gravity and atmospheric drag. Orbital insertion, when engines fire at precise moments to capture into orbit around another world. And course corrections, when even small adjustments need to be executed flawlessly because there's no second chance millions of kilometers from home. These are the moments when systems spin up, when redundant computers come online to double-check calculations, when gyroscopes stabilize the spacecraft's orientation, when power systems shift from idle to active mode, feeding energy to thrusters or communication arrays. There's a sequence to it, a choreography of activation that happens in a specific order because each system depends on the ones before it. What we're seeing with 3I/Atlas looks remarkably like that kind of systematic activation. The wobble in the anti-tail, the oscillation we first detected about a week ago, started at a frequency of roughly one complete cycle every 8.2 hours. That was unusual enough. But over the past 72 hours, that frequency has been increasing, not erratically, as you might expect if the object were tumbling faster, due to outgassing jets pushing unevenly on its surface. The acceleration is smooth, steady. predictable. As of the most recent measurements, taken by the European Southern Observatory's Very Large Telescope Array in Chile about 18 hours ago, the wobble frequency has increased to 1 cycle every 6.7 hours. That's a 22% increase in oscillation speed over just 1 week. For a structure that size, remember, we're talking about something extending more than 400,000 kilometers to change its oscillation frequency requires an enormous change in the forces acting on it. Either the structure itself is being actively driven by some internal mechanism, or the mass distribution is changing in ways that alter how it responds to external forces. Natural systems don't do this. Natural systems tend toward equilibrium. A pendulum swings at a frequency determined by its length and the local gravity. You can't make it swing faster unless you add energy to the system. A spinning object rotates at a rate determined by its angular momentum and moment of inertia. It can speed up if mass moves inward, like a figure skater pulling their arms in during a spin, but that requires internal structure and control. 3I/Atlas is speeding up its wobble. Something is feeding energy into that oscillation. Something is driving the frequency higher as we approach December 19th. What does that acceleration curve look like if you plot the wobble frequency over time? You don't get a straight line. You get an exponential curve. The rate of increase is itself increasing. It's not just spinning up, it's accelerating its spin up. That's the signature of a powered system approaching operational capacity, like an aircraft engine spooling up for takeoff or a particle accelerator ramping up to full power. There's another change happening simultaneously. The thermal signature. Infrared observations from the James Webb Space Telescope, which has been periodically observing 3I/Atlas, as part of a broader survey of interstellar objects, show temperature variations that don't match the expected pattern for a passive comet. When a comet absorbs sunlight, it heats up. When it's in shadow or moving away from the sun, it cools down. The temperature profile should follow the solar flux very closely, with some lag due to the time it takes for heat to penetrate into the ice and rock. 3I/Atlas is showing temperature spikes that don't correlate with its distance from the sun. These aren't random fluctuations, they're localized hotspots, appearing in specific regions of the object, lasting for hours before fading. And they're becoming more frequent as the wobble frequency increases. Hotspots on a comet can occur naturally when fresh ice is exposed and suddenly begins to vaporize, releasing stored heat, but these hotspots are appearing on the night side of the object, the side facing away from the sun. Where no direct solar heating is occurring, that's not where you'd expect outgassing activity. What you would expect, if you had internal power systems activating, is exactly this kind of thermal signature: waste heat from generators. Heat from electrical systems coming online. The same way your laptop gets warmer when you're running intensive programs. Or how a car's engine compartment radiates heat even after you park and turn the engine off. The correlation between the thermal spikes and the wobble acceleration is too precise to ignore. When the wobble frequency jumps, a thermal spike appears within the next few hours. The object is consuming energy. It's converting that energy into mechanical motion, the wobble, and producing heat as a byproduct. Think about what we established earlier. The object has been absorbing sunlight with remarkable efficiency. It's been in the inner solar system, bathed in solar radiation, for months. If it's equipped with any kind of energy collection system, solar panels, thermal collectors, something we haven't even conceived of yet, it's been charging, storing power, building reserves. And now, as it approaches the critical date, as the geometry aligns and the transmission window opens, it's beginning to spend that stored energy on what the most obvious answer is: propulsion. If you need to make fine adjustments to your trajectory, if you need to ensure you're in exactly the right position at exactly the right time for that 4-hour window on December 19th, you need to fire thrusters. You need to make course corrections, and those corrections would produce exactly the kind of acceleration we're seeing in the wobble pattern. The anti-tail structure responding to thrust, oscillating faster as repeated small burns adjust the object's path. But there's another possibility. The energy might be going into the transmission system itself. If you're about to send a massive data package across 26,000 light years of space, you need power. A lot of power. Radio signals weaken with distance according to the inverse square law. Double the distance, and the signal strength drops to 1/4. The power required to send a detectable signal to the galactic center, even using our planet as a gravitational lens, would be extraordinary. Our most powerful radio transmitter, the Arecibo Observatory before its collapse in 2020, could broadcast at 1 megawatt. That signal could theoretically be detected by a similar-sized antenna up to 1000 light-years away under ideal conditions. To reach 26,000 light-years, 26 times farther, you'd need roughly 676 times more power. That's 676 megawatts, equivalent to a large nuclear power plant. If 3I/Atlas has been collecting and storing solar energy for months, and it's now activating those reserves, the thermal signatures and the wobble acceleration both suggest we're watching a system come online. A system designed for a very specific task. A task that requires careful positioning, enormous amounts of power, and precise timing. A task that reaches its critical moment in less than 48 hours. But before that moment arrives, there's something else we need to understand. Something that suggests the object isn't just preparing to transmit, it might be preparing to receive. Communication across interstellar distances is one of the hardest problems in space exploration. When NASA's Voyager 1 spacecraft, now more than 24 billion kilometers from Earth, sends a signal home, that radio wave travels at the speed of light and takes about 22 hours to reach us. The signal is incredibly weak by the time it arrives, about 20 watts when it left the spacecraft. Reduced to a whisper of a billionth of a watt by the time it reaches our antennas. We can only detect it because we have enormous dish antennas, like the 70-meter dishes of the Deep Space Network, constantly listening. Now imagine sending a signal not 24 billion kilometers, but 26,000 light-years. That's roughly 246 quintillion kilometers. The same signal that takes 22 hours to reach us from Voyager would take 26,000 years to cross that distance. If 3I/Atlas sent a message when it first entered our solar system, let's say 8 months ago when it was first detected, that signal is only 0.00031% of the way to the galactic center right now. It wouldn't arrive for another 25,999 years, give or take a few decades. So when unusual radio signatures were detected by the Deep Space Network 3 days ago faint, structured signals that appeared to be directed towards 3I/Atlas rather than coming from it, the immediate reaction from astronomers was skepticism. The timing made no sense. There hadn't been enough time for any message from the object to reach the galactic center and for a response to come back. Unless the response wasn't coming from the galactic center, the Deep Space Network NASA's array of giant radio antennas positioned in California, Spain, and Australia to maintain constant contact with spacecraft regardless of Earth's rotation wasn't originally pointed at 3I/Atlas. The dishes were tracking various missions, Mars rovers, the Juno spacecraft at Jupiter, New Horizons in the Kuiper Belt. But the network also runs continuous background scans, recording all radio signals in the regions of sky it's monitoring. During a routine data review, technicians notice something in the background noise, a signal in a frequency band that's typically quiet, not from 3I/Atlas's position, but from a point in space roughly 15 degrees away from the object. The signal lasted approximately 8 minutes, Then it stopped. 8 minutes is significant in astronomical terms. That's roughly the time it takes light to travel from the Sun to Earth. It's also, coincidentally, about the time it takes for a radio signal to travel from Jupiter to Earth when the planets are relatively close together. The duration suggests the signal travelled a specific distance, was received and processed, and then terminated when whatever was receiving it finished recording the message. The frequency signature didn't match any known spacecraft. It wasn't one of our probes, it wasn't commercial satellite traffic. And the directional analysis, the determination of where the signal was coming from based on which Deep Space Network station detected it, most strongly placed the source somewhere beyond Mars's orbit but inside the asteroid belt. That's empty space. There are no planets there, no large asteroids in that particular region, no missions currently active in that area. But if you were designing an interstellar network, if you wanted to send probes across the galaxy without requiring 26,000-year response times, how would you do it? You'd build relay stations. You'd position receivers at intervals along common travel routes. When a probe sends data, it doesn't transmit all the way back to home, it sends to the nearest relay. That relay amplifies and retransmits the signal to the next relay, and so on, creating a chain that eventually delivers the message back to its origin. It's the same principle behind our own telecommunications infrastructure. Your cell phone doesn't transmit directly to your friend's phone across the country. It sends to a nearby tower, which routes through a network. If there's a relay station in our solar system, something positioned in the asteroid belt, something small enough that we haven't detected it through normal observations, then the communication timeline makes sense. 3I/Atlas has been transmitting data for weeks, perhaps months. That data has been travelling at light speed to a receiver station a few 100 million kilometres away. 8 minutes of transmission time suggests significant data volume. Possibly terabytes of information about what the probe has observed in our solar system, spectra of our planets, measurements of Earth's atmosphere, radio emissions analysis showing electromagnetic signatures of technological civilization, a complete survey of our system and what it contains. The signal that was detected wasn't random noise. When radio astronomers analysed its structure looking at how the power varied over time, whether there were patterns in the frequency modulation, they found characteristics that resembled compressed data packets, the kind of signal you'd see when information is being transmitted efficiently, encoded to maximise the amount of data that can be sent in the shortest possible time. And here's what makes this particularly striking. The signal appeared to be directed back toward 3I/Atlas. Communication is a two-way process. If you're a probe transmitting a report, you also need to be capable of receiving instructions, updates to your mission parameters, course corrections, new targets to investigate, or perhaps simply an acknowledgement that your data was received, that everything is functioning as designed, that you should continue with a planned sequence of operations. The SETI Institute, the organization dedicated to searching for extraterrestrial intelligence, has protocols for what to do if we detect a signal from space. Step 1 is confirmation. You verify it's not a mistake, not interference from satellites or Earth-based transmitters. Step 2 is triangulation. You get multiple observatories to detect the same signal and determine exactly where it's coming from. Step 3 is analysis. You try to decode the signal, understand its structure, determine if it carries information. What the SETI Institute doesn't have protocols for is what to do when you detect a signal being sent to an object that's already in your solar system. When the confirmation isn't there's something out there, but there's something out there talking to something in here. The response to 3I/Atlas, if that's what it was, raises questions that go beyond this single object. If there's a relay network, how extensive is it? How many stations are they only in our solar system? Or are they scattered throughout local space, creating an infrastructure we've been moving through without ever noticing? And more urgently, what did the response say? Was it a simple acknowledgement, a confirmation that data was received? Or was it something more active? A set of new instructions? A command sequence for what happens after December 19th? Because the timing of this response, coming just 3 days before the closest approach to Earth, suggests that whatever 3i/Atlas is preparing to do, it might not be operating purely on pre-programmed instructions anymore. There's a curious pattern in how space agencies communicate with the public during unusual events. When the Perseverance rover lands on Mars, NASA broadcasts live. When the James Webb Space Telescope captures a stunning image of a distant galaxy, it's released with detailed explanations and press conferences. When Voyager 1 crosses into interstellar space, we get updates, interviews with scientists, graphics showing the spacecraft's position relative to the solar system. Transparency is the default. That's how science works. That's how public institutions funded by taxpayers maintain trust. But when something doesn't fit the expected narrative when data comes back, that challenges our understanding in ways that might cause public concern, the communication strategy changes. Updates become less frequent. Technical details are withheld pending further analysis. Press releases emphasize the mundane while omitting the extraordinary. With 3i/Atlas, we're seeing that shift happen in real time. The object was first announced to the public in late March 2025, about 3 weeks after its initial detection by the asteroid terrestrial impact last alert system in Hawaii, the same survey that discovered the first confirmed interstellar visitor, 1i/Oumuamua, back in 2017. The announcement characterized 3i/Atlas as a likely interstellar comet showing typical outgassing behavior. The Minor Planet Center issued a circular. A few astronomy news sites ran brief articles. It was treated as interesting but not exceptional. Then, for nearly 2 months, there was silence. No follow-up observations were published. No updates on the object's brightness or trajectory refinements. This is unusual for an interstellar visitor. When 2i/Borisov, the second confirmed interstellar object, passed through our system in 2019, there were weekly updates, dozens of papers analysing its composition, its orbit, its outgassing patterns. The astronomical community was energised, collaborative, transparent. The silence around 3i/Atlas only broke in early June when amateur astronomers using their own equipment, sharing data through online networks, started publishing observations that didn't match the typical comet description. That's when the anti-tail was first noticed. That's when people started asking questions about the wobble, about the brightness variations, about the spectroscopic anomalies. And the response from major institutions was measured, cautious. Papers began appearing on the Arxiv preprint server, the platform where researchers share findings before formal peer review, but many of these papers were authored by independent scientists or small research groups. Not the large collaborations you'd expect for an object this significant, not the teams from NASA, ESA, or major universities that typically lead interstellar object research. Why? One possibility is that the data is simply complex. It requires careful analysis. Rushing to conclusions would be irresponsible, especially if those conclusions challenge fundamental assumptions about what interstellar objects can be. Scientists are naturally conservative. They want to be certain before making bold claims. But there's another pattern worth noting. Several researchers who've been vocal about the anomalies posting their findings on social media, giving interviews to science journalists. Speaking at virtual conferences have reported being approached by colleagues suggesting they wait for more data before publishing. not because the analysis is flawed, but because the implications are premature. Dr. Loeb has been an exception to this caution. His willingness to discuss the possibility that 3/Atlas might be artificial, that it might represent technology rather than nature, has made him a lightning rod for criticism within the astronomical community. Some of that criticism is legitimate scientific skepticism. Extraordinary claims require extraordinary evidence, as Carl Sagan famously said. But some of it feels less like skepticism and more like discomfort with where the evidence is pointing. Consider what we know from public data sources. The trajectory of 3/Atlas has been refined multiple times as more observations accumulate. This is normal. But if you compare the published orbital elements, the mathematical description of the object's path through space between March and June, something interesting emerges. The trajectory changed. Not by much. We're talking about tiny adjustments, fractions of a degree in the orbital inclination, small variations in the perihelion distance. Within the margin of error for initial observations, according to the official statements. But multiple amateur astronomers, working independently, have noted that the refined trajectory seems optimized for the December 19th Earth flyby in ways that the original trajectory wasn't. It's as if the object adjusted its course. Natural objects don't do that. Comets can experience slight trajectory changes from outgassing jets of vapor acting like tiny rocket engines, but those changes are typically random and difficult to predict. They make the orbit less certain over time, not more refined. The trajectory refinements for 3/Atlas suggest the opposite. The path is becoming more precise, more clearly aimed at a specific close approach date, as if corrections were made deliberately. When questioned about this, astronomers from the institutions tracking the object have pointed to the complexity of calculating orbits for active comets. They emphasize that the early trajectory estimates were based on limited data and that the refinements simply reflect better observations, not actual changes in the object's path. That explanation is plausible. It might even be entirely correct. But it's also the explanation you'd give if you wanted to avoid discussing the possibility of course corrections. There's also been a curious silence around observation requests. Major telescopes Hubble, James Webb, the Very Large Telescope Array in Chile allocate time through competitive proposals. Researchers submit requests months in advance, explaining what they want to observe and why. For an object as unprecedented as 3/Atlas, you'd expect observation time to be heavily contested. You'd expect dozens of approved proposals, with the results being published as data comes in. But searching through the public databases that list scheduled observations, 3/Atlas appears far less frequently than you'd expect. Some of this might be timing the object's position in the sky, the availability of telescopes, competing priorities. But some astronomers have privately mentioned that their proposals to observe 3/Atlas were declined or delayed, sometimes without the usual detailed feedback about why. Again, this could be innocent. Telescope time is precious. Not every proposal gets approved. But the pattern reduced institutional transparency, cautious public statements, observation access that seems more restricted than expected creates an impression that there's a deliberate effort to control the flow of information. Or perhaps it's simpler than that. Perhaps the institutions themselves are uncertain. They're seeing the same data we've been discussing: the wobble, the spectroscopic anomalies, the thermal signatures, the trajectory refinements. They recognize that these observations don't easily fit into the natural comet framework, but they also recognize that claiming artificial origin without absolute proof would be the most significant scientific announcement in human history. The burden of proof is enormous. The consequences of being wrong are severe. So they wait, They gather more data, they run more analyses, they consult privately rather than publicly, and in the meantime, December 19th approaches. The object continues its careful, precise approach to Earth. And the question that no official statement has directly addressed remains unanswered if this isn't a comet. If the evidence increasingly suggests something designed rather than natural, what exactly is about to happen when it reaches its closest approach? Every spacecraft mission has an end-of-mission plan. When Cassini completed its 13-year exploration of Saturn, NASA didn't just let it drift into space. They commanded it to plunge into Saturn's atmosphere, ensuring it wouldn't accidentally contaminate any of the moons that might harbour life. When the Mars Opportunity rover finally succumbed to a dust storm after 14 years of operation, mission controllers sent a final series of commands, hoping to re-establish contact, before officially declaring the mission complete. The point is, designed objects follow designed plans. They have purposes, and when those purposes are fulfilled, something happens next. Either they continue to a secondary objective, or they shut down, or they're deliberately disposed of in a way that serves some final function. If 3I/Atlas is what the evidence increasingly suggests a probe, a surveyor, a messenger, then December 19th isn't its endpoint, it's a milestone. And what comes after that milestone depends on what the object was designed to do. Let's consider the most optimistic scenario first, the Flyby scenario. In this interpretation, 3I/Atlas is purely a reconnaissance probe. It entered our solar system, gathered data about our star, our planets, our chemical compositions, our electromagnetic signatures. It's been transmitting this information back through whatever relay network exists, reporting its findings to whoever sent it. On December 19th, it completes its close approach to Earth, the final item on its survey checklist, and then continues outward. It leaves our solar system the same way it entered, coasting on its original trajectory, perhaps heading towards another star system where it will repeat this same process. In 1,000 years, it's light years away, and Earth becomes just one entry in a vast catalogue of surveyed systems. This scenario has precedent. This is exactly what our Voyager probes are doing right now. They completed their primary missions decades ago, studied Jupiter and Saturn, and then continued outward into interstellar space. They're still transmitting, still sending back data about the boundary between our solar system and the space between stars, until their power finally runs out sometime in the 2030s. If 3I/Atlas is a von Neumann probe, a self-replicating spacecraft that visits star systems, gathers resources, builds copies of itself, and sends those copies to new destinations, then a simple flyby makes sense. No need to linger, the mission is observation, not interaction, collect the data and move on. But there's a second scenario that the trajectory data supports. The parking orbit scenario. When you look at the refined orbital calculations, the updated predictions for where 3I/Atlas will be after December 19th, something interesting appears. The object's path after Earth flyby shows characteristics that could, with relatively minor adjustments, result in a gravitational capture. Not around Earth directly, the object is moving too fast and approaching at the wrong angle for that, but potentially into an elongated orbit around the Sun that keeps it within the inner solar system. This would require course corrections, small burns at specific points to bleed off velocity, to change the orbital inclination just enough to avoid being ejected back into interstellar space. And we've already discussed evidence that suggests 3I/Atlas is capable of making exactly these kinds of adjustments. The trajectory refinements, the wobble pattern that looks like thrust vectoring, the thermal signatures consistent with active propulsion systems. If the object enters a parking orbit, perhaps a highly elliptical path that takes it from the inner solar system out to the asteroid belt and back. With an orbital period of a few years, then it's not leaving. It's taking up residence, continuing to observe, continuing to transmit, becoming a permanent fixture in our neighbourhood of space. Why would you do that? What would justify the energy expenditure of staying rather than continuing your journey? The answer might be because you found something interesting, something worth extended observation. Earth is unique in our solar system in one obvious way. We're the only planet with detectable technosignatures, radio transmissions, atmospheric pollution, artificial lighting visible from space, organised geometric structures that can be seen in satellite imagery. If you're a probe designed to catalogue solar systems, and most of those systems are empty of technological life, then finding one that isn't would trigger a different protocol. Extended monitoring, detailed study, perhaps waiting to see how the civilization develops, how it responds to challenges, whether it becomes spacefaring or destroys itself. That's not a comforting thought. The idea that we're under observation, that something has decided we're worth watching, carries implications about our place in the universe that humanity hasn't fully prepared for. But there's a third scenario, the one that researchers discuss quietly in private conversations, because publicly suggesting it invites ridicule even though the evidence doesn't rule it out. The response scenario. What if the signal detected 3 days ago, that 8-minute transmission from somewhere in the asteroid belt directed toward 3I/8LAS wasn't an acknowledgement of data received? What if it was a command sequence, new instructions based on what the probe has observed, instructions that change what happens on December 19th? In this scenario, 3I/8LAS was launched with a primary mission profile survey the system, report findings, continue outward. But the mission design included flexibility, conditional instructions. If certain criteria are met, if you detect electromagnetic signatures consistent with technological civilization, if spectroscopic analysis of the third planet shows atmospheric chemical imbalances consistent with industrial activity, if radio observations reveal structured communications, then activate secondary protocols. Those secondary protocols might involve anything: deploying additional sensors, releasing smaller probes that can approach Earth more closely, broadcasting a message directly to us, now that the presence of technological civilization has been confirmed, or, more provocatively, initiating contact procedures. This is where we enter territory that lacks historical precedent. We've never been in this position before. We've never detected something approaching our planet that shows evidence of being designed, controlled, purposeful. We don't know what the protocols for such an object would be. We're writing the playbook as we go. What we do know is this December 19th represents a convergence. The geometry is optimal for transmission. The power reserves are at maximum. The wobble frequency has accelerated to levels that suggest active systems operating near capacity. And most critically, the object has received external communication, whatever that signal from the asteroid belt contained within the window, where it could still alter its behaviour for the close approach. So as we count down these final hours, and we are now measuring time in hours, not days, the question isn't just what will happen, the question is what has already been decided. Because the object isn't improvising, it's following a plan that was set in motion long before it entered our solar system, possibly centuries or millennia ago. A plan that has brought it precisely to this moment, to this alignment, to this distance from Earth. And that plan is about to unfold.